relevant points from the last lecture. So we were discussing the evaporation of this eternal black hole by evaporating both sides into these external systems, the bath, as I've been calling them. When computing the entropy, it was convenient to give this picture an alternative interpretation, which is what is shown in the second picture, where we replace the ADS2 bulk by these two 0+1 quantum mechanical systems, which I call L and R. And here I'm computing the entropy of the bath, the von Neumann entropy of the bath, let me start again. Here there are various notions of entropy. The constant horizontal line, SBH, that is the Bekenstein-Hawking entropy as measured from the LR perspective. That's essentially just the size of the black hole as a function of time. And this is a static situation, so it's just constant. S radiation, that is the von Neumann entropy of the baths, where we time evolve both baths symmetrically, upwards in time. And we saw that this system has an information paradox, namely that the von Neumann entropy of the bath exceeds the coarse-grained entropy. And we said that if this theory was a unitary theory, then we expect the Page curve, something that looks like this curve that is the minimum of the coarse-grained entropy and the entropy of the fine-grained entropy of the radiation. So it should grow and then at some point become constant once the left-right system, once the room for entanglement in the left-right system is capped out. Okay, and now I'm going to talk about consequences of assuming that indeed we have a Page curve. So consequences for unitarity. And the last thing I emphasized was that if one was to reproduce this Page curve for both the left-right system and for the bath system, then that is tantamount to resolving the information paradox. But before we get there, let me continue. Actually, before that even, are there any questions about this?
Yeah. It seems to me saying tantamount to resolving the information paradox is too strong. Accurate version would be tantamount to removing one of the. The information paradox, you will have to actually show that each state leads to different radiation.
Good point. Yes. So tantamount to resolving the information paradox as stated by Hawking, which is just simply that the von Neumann entropy just continues to increase. But after this, but that's not sufficient. I agree to display full unitarity. You need this one-to-one map between initial and final states. Completely agree. Yeah. And I guess a related thing which will come in later will be, for example, understanding the black hole physics of the black hole interior and so on and so forth. That's all related, and we'll get there. Any other questions? Okay. Do you guys need the mic other than recording? 'Cause it seems loud. These guys are gone. It is.
But without the microphone, the recording doesn't. It's only doing the recording.
I think he's talking about the loudspeakers.
I'm talking about the loudspeakers. It doesn't feel as close as the other lecture. Like it's. Yeah. Well,
or if you are sure it won't jeopardize the recording.
Yeah.
Is it okay to turn off the speakers? Like they can hear me. It's fine.
They are recording actually.
No,
I will reduce your mic.
yeah. Just reduce the volume.
But it should not interfere with the recording.
Yes,
Yeah. Feels like I'm delivering a lecture. Like. Yeah. In the meantime, any other questions? Good. Okay, so before we get to these other ideas, yeah.
Can
Oh,
you
good.
clarify this point? When you say the stronger thing would be to take all the initial state and say what is the final state?
Yes.
And compared to here, what do I learn about?
So in this case, it would be something like, this is awesome. So I can have different states of this eternal black hole. I can have particles, for example, floating inside, and that should ultimately map to a different state of the baths, for example. In fact, this is related to the next thing I'm going to say, which is that if you were to throw information into this black hole, so at some point here, throw some information, at some point you should be able to recover this information from the Hawking radiation, which in this case is some state of the bath at late times. Okay? I'll try to convince you that this has to be true. I mean, it's not so clear in this case, right? Because so for an evaporating black hole, it disappears, or it converts, it transforms from that shell that you throw in into just the radiation. So clearly the information that fell in has to be in the radiation. But here the black hole is there for all time. So it's not really clear that the information that you've thrown in has to appear there. One can imagine, although maybe just imagine, I don't think this is true. One can imagine that maybe the entropy, you can find a model in which the entropy is constant, as in it does what you want it to do, but the information stays inside. Maybe that can happen. But I think, but perhaps the next thing I'm going to say precludes that and actually proves that the information has to go out.
I mean, it almost seems like it would preclude it because otherwise you could keep feeding information in.
Oh yeah, exactly. That's essentially, I think, the argument that I'm going to give now.
So reconstructing the information does not mean that you can deduce the quantum state of the particle that was thrown in, right? It's something less than that.
No, I think it's the same thing. I think it's the
You
same.
mean to say that you can actually reconstruct
The state of the thing that you threw in.
So something, a lot of correlators or something. Just the entropy, of course, is too crude.
But no, but literally, as I said, you should be able to find a one-to-one map between these initial states and the final states.
I think what I'm saying, if you just know the entanglement entropy of the outside, that will not do it.
Yes.
You want to know the state of the bath at late times.
Yeah, yeah.
So the observables will be much finer. I mean,
That's right. Definitely. That's definitely.
And Ahmed, you're probably leading up to this, but just to say, do tell us a little bit about Preskel, Hayden.
That's the next thing. That's the next thing.
And all that.
That's the next thing.
Connection which has to be with the chaos bound, which no
Chaos.
one talks about, but
Maybe there's something there. I don't.
the chaos bound also has the same exponent, etc. So is there anyway?
Okay,
all
okay,
your
okay.
thoughts there would be great.
Okay. So next up is the Hayden-Preskel protocol. The idea is to first show that information thrown in appears in the Hawking radiation, and there's also the question of how long does one need to wait for a message thrown into this black hole to appear in the Hawking radiation. As a prerequisite to, so I'm going to draw circuit diagrams. So first of all, so this is the process that we have. So the black hole is kept in equilibrium, but let's describe the process that goes on that keeps it in equilibrium. So something that happens is, so this is the black hole and that's the radiation. We see what happens is that the black hole loses a qubit, but then it gains a qubit. Okay, that's how the black hole mass is maintained. Okay? So we want to draw a circuit diagram which reflects this.
How does it lose the qubit?
It escapes from the ADS2 region into the bath region. That's just the Hawking radiation going out. And then you also have Hawking radiation coming in. Okay. As a prerequisite, first I need to Or
Sorry, this just keeps happening in the thermal vacuum.
yes, exactly. Yeah, so let me draw the circuit diagram for this. I can draw it here. I should say that we are looking at, let's imagine looking at the setup at late times, somewhere here, past the page time. So at this point, you would say that the black hole is already maximally entangled with the radiation, okay? Okay, so let's draw the circuit diagram. So
Sorry, I should ask earlier. What was special about t equals 0 in this diagram?
here,
Yes.
yeah,
Why did it start so low?
why does it start so low?
And how
That's a special feature of the thermal field double at t equals 0.
at a negative time it's symmetric.
It's symmetric, exactly. So now we want to draw a circuit diagram for this process. So first of all, we have an entangled. So these lines represent maximally entangled qubits.
So somehow t equals 0, you created the state, some very atypical state,
Yes,
and it equilibrates in both directions.
exactly. So in terms of energy, it's already equilibrated, but it tends to a more generic state. Maybe that's the one way to say it. Okay, so here, these 4 qubits, let's think of these all as the system LR, and they are entangled with BLBR. Okay? The black hole is maximally entangled with the radiation. Now let's imagine that there is some scrambling, well, there's some unitary transformation, which I'm going to represent by this block. I'm going to ignore the dynamics of the bath. I'm just going to draw this as just a straight line. So some trivial evolution. It doesn't really care. It doesn't really matter.
So BL and BR are the bath, and L and R are what?
They are the ADS2 region. They're the black hole system. Just think of it like that. So they correspond to these dual boundary theories at the asymptotic ADS2 region. Okay. So now we imagine that, so we said that the black hole loses a qubit. So there's one qubit that comes out, and it joins the bath in this way. And then we have these other 3 qubits. But it also gains a qubit. Okay, so is that clear? So this is supposed to describe this fact that I just said. You lose one and you gain one.
The gain is also shown as going upward, is it? I mean, just
The gain is the fact that you have these 2 qubits that are entangled. So you gain a qubit, but that qubit that you gain is entangled with something in the path. That's represented by this qubit and this qubit being joined in this way.
It's not some old qubit in the world?
It could be an old qubit in the bath. Think of it as 2 qubits coming in like this and one just joins. Yeah. Okay?
Voltage in the bath is increasing because just radiation is coming out.
It's actually infinite. There are many, many qubits here. And you're taking one pair of each qubit and you're throwing it in there as a function of time. So let's just draw another one. Okay. And then let me just draw it. Okay. So this describes this process. Now let's imagine we throw some information into the black hole.
What does that mean?
You could either think of you're preparing when preparing the path integral, you add some operator insertion near t equals 0 here. So, okay. the initial state is different. You're preparing a different initial state with a particle there. That's one way to think about it. Or you imagine that that you work with you act with an operator here on the left.
A bath operator.
It could be a bath operator or an L operator. L operator is more appropriate here.
Yeah, okay, L or R operator.
Oh, sorry, R operator, R, yeah.
Yeah. But, I mean, equally well, you could think of just the stuff coming in from the bath and hitting the boundary.
Yeah.
In effect, triggering the operator.
Okay, so that will be represented by, say, these 3 qubits. Okay, so let me call this M for the message. Okay. Now, if I add these 3 qubits, the size of L is larger. The size of LR is larger, so I need to include 3 more qubits here. 3 more qubits there. 3 more qubits there. Okay.
What are qubits? I mean,
Oh,
before this was really precise. This sounds like some cartoon.
Yeah, no, I am trying to give you a quantum mechanical model that,
Well, what is a qubit? I mean, there's a bath. It's a quantum field theory. What are qubits?
no, I'm right now representing the bath. I'm representing the bath. I'm thinking in this case the bath as some finite dimensional system,
Okay.
where and the LR is also another finite dimensional system, and I'm working with qubits, and I'm just trying to show that even in the case where you leave LR in some sort of equilibrium in terms of its number of qubits, that's like saying that it's like in thermal equilibrium.
Sorry, are you changing the number of qubits in the Hilbert space, or are you exciting one of the qubits? What does it mean that you're adding 3 new things?
I mean, you can think of it as exciting 3 more.
I think, I mean, what you would call in quantum field theory as exciting, you can think of from this perspective as adding. Namely, suppose you send a photon in.
Yes, exactly.
That's like adding a qubit. But you could say that, okay, you were in the vacuum and you excited it.
Okay, so I'm thinking of it as exciting 3 new degrees.
Yes.
Okay, fine.
And same on the right? I mean, here also, it
Yeah.
doesn't mean that the number of qubits keeps increasing, but rather new EPR pairs are being formed. So with some existing on the right hand side, you are creating an entangled.
There are 2 ways to think about this. Either as a new pair keeps getting formed as a function of time, or that this bath has a reservoir of entangled qubits like this. I add however many I want.
Yeah.
And this process is just a statement that I take one of these guys and I join it in. That's like throwing it into the black hole. That's how I get this. That's just me taking this guy and I join it there.
Yeah, so new entanglement is being created.
Yes.
Right? I mean, I don't. So the dimension of the Hilbert space of this BLBR stuff remains the same.
Yes. Yeah.
Is there any a priori reason to expect that the phase curve meets the black hole entropy? It could be below that also, right? I mean, the maximal.
That's right.
may not take place also.
That's right. But there's often there's an expectation that these systems are governed by some sort of chaotic Hamiltonian, and that's expected to always saturate the entropy.
But in the other case where it does not, let's say possibly, then you could have information never coming out.
Yeah. Although, so we expect that the state of LR tends to the thermal density matrix, actually. So if it does that, then you expect that the entropy, the fine-grained entropy will match the coarse-grained entropy. So you really will tend to that.
Isn't that a statement of the second law of Fibonacci?
Yes, essentially, yes. Okay, okay. Okay. I promise you this will be the only toy model in this doc. Okay.
I mean, in some sense, if this M, let's say in that box, is not talking to the other guys, then that just continues, and then that will lead to a picture where this curve is below that, right? You don't know.
Yeah, sure.
It is decoupled.
Exactly.
That would be an extreme case where that just is not talking to that.
That's right. But now I will convince you that if you choose a specific kind of box for these unitary transformations, then you can show that the information about M actually is going to be encoded here. Okay? So as a prerequisite for that, I need to give you or tell you about random tensors very, very briefly. So, say, okay, here's a random tensor. The statement is that, so a random tensor, let's say it has 4 legs. The statement is that this thing prepares a random state of these 4 qubits. This thing can have an alternative interpretation as some sort of map between, say, 1 qubit and 3 qubits. So I take one of these qubits and I drag it downwards. This defines an isometry from 1 to 3. So for given any state of 1 qubit, you can get you will get some state of these 3 qubits. So it's a map. It's a map of the 1 qubit Hilbert space to a subspace of the 3 qubit Hilbert space. If you take 2,
And it's a unitary map.
no, it's an isometry. But if you take 2 to 2, then it becomes a unitary map. And all these statements are true to some degree.
So an isometry is just any map, is it?
Yeah, it's a one-to-one map.
Oh, it's a one-to-one.
It's a one-to-one map, but you're mapping this Hilbert space to a subspace there.
Oh, yes, of course.
Yeah.
Yes.
Okay. The idea here is that
But it's a map that preserves inner products.
yes,
Yeah, that's what I meant by it.
I think that's what isometry means, or maybe. The idea is that, but yeah, okay, good. I'm going to make the following. So because it's a map from 2 to 2, this actually means that you can think of it, that you can think of this tensor as, or these statements allow you to push information through this tensor. Say you have this qubit and you want to push the information about this qubit into this tensor. You can make it come out of any 2 other qubits. So pushing it here, you say that the information comes out there. Because for any fixed state of this, it's an isometry from this guy to these 2. Okay? So I'm going to use this trick to show you that information about M appears here.
I did understand. Please say it once more.
Okay.
The random tensor is what? It's just I think I understood those two.
Okay, let's talk about this thing, this case. So we said it's a unitary from here to here.
Yes.
If I fix the state of this qubit,
For any choice of
any choice of 2 legs, exactly. This is a unitary from these 2 to these 2. This means if I fix the state of this qubit,
Yes.
then it's an isometry from this guy to these 2.
Yes.
It is this trick that I will use in the context there.
And leftmost diagram is what? It's just you have to fix nothing and you get a 4-qubit state.
Exactly.
It's a particular 4-qubit state.
Exactly.
Okay.
But now I'm going to use this idea here that I said that I can push this there, sort of independent of where the legs are. So the fact that legs are all up, or 3 up and 1 down, or 2 up, 2 down, doesn't matter. So I say the statement that I was just saying here is this statement, that I can push this leg into these 2.
That was a particular 4-qubit state. What does it mean?
No, you should not think of it as a state anymore. You should think of it as just some tensor, and information goes through this tensor.
I don't understand what
it's
tensor.
a map on 4-qubit Hilbert space. You put in things and you get number.
But now you've got nothing to put out.
Yeah.
Right?
So you can think of that like that. It's just a tensor with 4 indices.
Yes, yes, yes.
So now you think of this as one down index. You're inputting one and getting 3 out.
Okay.
It's a tensor with 4 legs, but if one or two of them have some values, then you get something for the other two.
Yes.
I think that's how.
That's how I'm thinking about it.
But it's a map from the Hilbert space to numbers. That first box. The 4-qubit Hilbert space to numbers.
Well,
It's a particular
um,
2 to the 4.
this,
It's a particular 2 to the 4-legged object.
So it's a map from the Hilbert space to numbers, right?
Yeah.
H to the 4th number.
yes,
You specify plus, down, minus,
Yeah.
plus, you get a number.
sure.
So may I think of the Thermophil double as an example of such a thing? A Thermophil double can be thought of as a state in a double Hilbert space. Alternatively, it can be thought of as a propagation, through the circle down.
This is the thermophil double.
Yeah,
It's a very special entangled state of.
yeah. If I cut my time slices, then it looks like a state in the like horizontally. Then it looks like a state in a double Hilbert space. On the other hand, if I cut it like angularly, then it's a propagation
Sure.
from a state in a single Hilbert space to another.
Something like this.
Yeah.
Yeah, yeah, yeah.
So this, when you say random tensor, is it really a generic tensor in the space of tensors, or it's a word?
Random tensor here means that you generate a random state of these 4 qubits. So you fix a basis of so you work in a specific qubit basis of these 4 qubits, and then you say that this prepares for you a random state.
And what is a random state? In that basis, it means everything appears with some distribution.
Random state that when you compute anything, when you want to compute any expectation value or whatever, you need to average over the Haar measure. That's what that means.
So I thought this tensor is a tensor, right?
Yeah, yeah.
From H to the 4 to a number, right?
Yeah.
So what is the random state now?
So no. Not sure I understood, but I mean, so okay, maybe I should. I mean, this thing is just some state.
It's a state, right?
Yeah, this thing is just some state.
State
A,
of
B,
what?
C, D of these
Right,
4
your
two.
map is taking partially number of elements,
Yeah, exactly.
right? Okay, that's.
Yeah.
And I think it's random, to tell me this right, it's random in the sense, suppose I trace over 2 of them and construct a density matrix for the remaining 2, that will be as random as it can be, sort of with maximal entanglement or something.
Yeah, but even
Partitions like this. At least that is part of the definition.
good. No, that's good. The statement is that any subsystem less than or equal to half has a maximally mixed density matrix. But that's actually, you can get that. So yeah, it doesn't have to be Haar random to guarantee that.
Our randomness probably guaranteed.
Yes, it is sufficient and more. Yeah.
Oh, it guarantees that.
Yeah, certainly guarantees that the row matrix will be as mixed as it can.
When you say isometry from 1 to 2, you are mapping this 1 dimension, 1 qubit Hilbert space to a subspace of the 3 qubits.
Yes.
Are you assuming very specific properties of the subspace, like it's some good subspace or something? You are not assuming. Are you assuming any property of the subspace?
I'm not.
You are not.
So just some subspace. But this point that I can push information through is essential for what I'm saying here. So let me just go through it, and if it's still confusing, we can talk more about it. Okay, so I just realized that this might be too small, but okay, let me do it anyways.
You know that you can roll the.
Yes. Okay, so let's push this information through the tensor network. Okay, so notice that each of these tensors has 14 legs. Okay, I don't know if you can count here. There's 4 and 3, 4 and 3. So let's push this information through. Oops. Okay. As I said over here, I can push the information of this 1 qubit into any half of the legs. So over here, I have to pick 7 legs where the arrows are coming out. Okay, that's, draw something like this. So I can pick these 4. There's a smart choice here. I'll choose these 4 and this one. So I've chosen 5 so far. So this already says that part of the information is in the bath. Okay. Okay, now I need to pick 2 more. So let me pick those 2. Okay. Those guys, I can propagate them up. So it's clear at this first stage that not all the information about the message appears in the bath. Some of it continues to propagate in sort of in the left-right system.
So is some of it meaning on the left thing also, right?
Yeah.
Things that you are not drawing the arrow on.
There it's coming in.
No, there it's going to be coming in. But we don't care about that for now. Okay, but I'm just keeping track of where the information about the message goes. Some of it is trapped in the left-right system, and some of it is in the bath system.
Sorry, I missed how do you separate the outgoing arrows from the one that you just said coming in?
So I'm,
The
but
property of this thing is as 3 go in, everything else takes that out.
not everything else. Any half. Any half.
Oh, okay, sorry, I missed that half.
Yeah, any half takes it out. So in this case, I picked the half that takes it out. So as Sandeep said, you can think of these 4 as coming in. So it's like I have 7 coming in and 7 coming out. Okay? But for now, I just want to keep track of the information about M. So I have these guys coming out. And again, let me emphasize the point is that not all the information about M went to the bath. Some of it is trapped in the left-right system. Let's go one more step.
And sorry, I mean, just to understand, this is because there is a unitary map between any 7 and any other 7.
Exactly. Exactly. Okay, so now I have these guys going up like that. And now let me do the same thing.
So does this diagram describe subsequent time steps as we go?
Yeah.
So in that case, the rest 4 that are incoming, so is something propagating from the past of the other 4 legs?
You can think of it like that if you want. It's just, yeah. But that's not essential, and it might be a bit confusing. Okay.
Think of it as for every choice of 4 states for those 4 legs, we get some information coming out of this.
That's going to be, and the state of these 4 states is going to be determined by this state over here.
So I think I missed the point. Was it an assumption that at least half of the legs are carrying the information? Why not just one?
No, so it's a feature. It's a feature of these random tensors.
So
That
this is an assumption, or does it follow from these claims about unitarity?
No, it's a feature. It's part of the it comes about from this definition that it's a random tensor.
It's definitions, it's an input. But, I mean,
It's a construction. I constructed something that prepares for me a random state in this way, and such things can be thought of as unitaries from any half to any half.
I think Indrajit is asking, is it clear that the physical problem has this feature?
It'll be a model.
It's a model for now, and it's the same model that what Hayden Preskel. Well, how about this? I'll get back to that, and the answer is yes, it is a good model. But I'll get back to that point in a sec.
And here you can choose any 7, you chose the best.
I chose the best. Exactly. So now I have 2 here. Let me choose another 7. So this guy. So I'll choose this guy to come out, this guy to come out, and let me see. This guy to come out. But now this might seem a bit confusing. I'm also going to pick these guys to come out. Okay? And which propagate down here.
Don't you want to prove it for the worst case? This is like the most favorable case. Don't you want?
Yeah, I can choose whichever partitioning I want. That comes in the definition of these guys. Okay, so then these guys come down like this, and Now going here, so now we do the process one more time. Notice how here there were 2 coming out from this tensor continuing up, but now there's only 1 coming out going to this tensor. Now let me do the same thing. So this guy goes in, now this guy comes out, this guy comes out. But now let me choose the rest as coming out here. And now we see that that's sufficient. This single qubit here maps to 1, 2, 3, 4, 5, 6, 7. So we're good. Now everything else, and that's it. We don't care about the rest of this process. So we see how the information from M here has been pushed, that's the technical term, to the bath. Okay? Good.
So sorry, I will ask the same question again. It was the most optimal way,
Yeah.
but what about other ways? Is it like that you take any possible choice to start with and then you will always lead to this eventually?
The question is how random does this tensor need to be?
Let's say we start with the one that you have, that half of them. Even with that definition, you started with the most optimal one, which is immediately pushing it out. In the first one, it was pushing some of them out.
You mean this feature here? This thing that I did here, like
In
this?
the above line, you have chosen the first rightmost 3
Uh-huh.
from my direction.
Yeah.
rightmost 3. Would have started with the leftmost 3.
Yes. If you can find a path from here to there, then that's all you need to do.
It works for any set.
Yeah, something will always have to go out.
For
because-
any choice of half number of lines.
Sorry, I haven't fully internalized. So we are particularly interested in those 3, right?
Yes.
And their path, right?
Yes.
So what you're saying is, if I look at their path,
Mm-hmm.
at the first stage, just to make sure,
Mhm.
in terms of what comes out, I should only look at the later instant of time, right? So I have 1, 2, 3 coming out, and out of them, 1 makes it out to the bath. That's how.
Not just one, and also part of this.
So I should also think of that.
Yeah.
So, so in other words, your point is, okay, if I consider the 3 going in, then altogether after some number of steps,
Yes. After some number of steps, it's contained in the bath.
I see, and just, I haven't quite, because even at the final step, there are some number of legs which aren't they going upwards?
No. These are all going inwards.
Or shouldn't 7 have been going?
Yeah. 1, 2, 3, 4, 5, 6, 7.
Sorry, first you started with these three M's. In the first step, why could you not put those 3s on the leftmost?
No,
It will take more time, so the time scale will
No, it won't actually take more time. It's this thing in quantum mechanics where, so if I give you a random state, so we said that any subsystem less than half is maximally entangled with any system greater than half. Okay? We're asking here about a particular division. So there's some smaller subsystem, which is like the message. We want to show that it's maximally entangled with the complement. For maybe this is not the best phrasing, but there's a particular thing that we want to show that is maximally entangled with something else. The fact that other divisions have smaller things maximally entangled with other bigger things is not relevant for us.
Sorry, this is a unitary between any 7 to any 7. So you can just choose any 7 you want.
What does this choice correspond to in the physical thing? Does it mean that it's a clever choice of the detector state? That, if I construct my detector to be sufficiently clever, then I can get quickly the information about this. What does this? So this choice means what?
No, how about this? Let me say something else. Let me see. worry this might be more confusing. Okay. So we have time, right? Time is not an issue.
But we have 4 lectures and we'd really like to get to the end of it. So my suggestion, my personal suggestion is that if there's something that's not,
It's not essential.
it's not essential, we can move on.
No, I was trying to see if I can give a different argument for this, but maybe that's not essential.
No, please do, of course, go as you like, but just to understand in terms of modeling the black hole system, the idea is that although you had 4 initially and you threw in 3 more, the idea is that you have a lot of qubits initially and then you throw in a few more. A lot of qubits initially in the LR system entangle very well with the BLDR. And then you throw in a few more and in a sense, because of the huge amount of entanglement you start with, you recover the 3 you throw in relatively easily, right?
That's right. That you only need to wait for sort of a number of steps, which is in some sense determined by the number of qubits that you've thrown in.
Yeah, these 3 very efficiently mix with everything on the LR system.
That's right.
And then get transported.
And
That's right.
therefore, as long as you get 1 qubit out at each step, you get out the 3.
That's right.
That is, no?
That's right.
That's what you illustrated.
Yes. So often this thing is phrased in the following way. One introduces an additional system, let's call it N, which is often called a reference system, which is maximally entangled with your message. This is sort of a way to encompass the case where you're sort of allowed to include the message in any state you want. By projecting N onto a specific thing, you project M onto a specific state. And so, yeah. The thing that one would need to show, the thing that my argument illustrates here is the following fact, that the density matrix of rho n LR approximately factorizes. This is a statement that there's no mutual information between N and LR, and therefore all the information is actually in the Bath system. Okay? Phrasing the things this way.
Okay, but you want to make that statement at the end, right? That is,
Yes.
you wait for a number of steps and then you measure rho and LR, right?
That's right.
As your diagnostic of
LR is, I guess, these qubits here.
just all of that.
Yes. Exactly.
Is random tensor, you can deduce the chaos exponent from this?
I don't know. It might be too much.
Yes, for the efficient randomization is key. If
Yeah.
it has to come up, you have to be at the
I
chaos.
mean, if it is slightly even less than random, right?
So-
If it is even a little less random, then it's difficult. Even a little bit less.
So I'll make a comment on that in a sec. So you can ask if you go through this process, and you ask how close is this, how true is this statement? So often you do a calculation that looks something like this. You integrate over U's. U's are like these matrices, these tensors here, and you compute in the one norm the difference between these density matrices, and you can show that this is given roughly by the dimension of M times the dimension of LR divided by the dimension of B. Okay?
Somehow you're taking some sufficient time evaluation also in this formula?
So in this formula, this depends on U. Okay? And I'll tell you where the time comes in a sec. So you here, this is a Haar integral, so I'm integrating over the Haar ensemble. And the place where the time comes in is in the following. Notice here the size of B is controlled by the number of steps that we went through, because you keep collecting these more qubits. And so you can write B in some sense as equal to LR times the radiation, the number of Hawking modes that escaped the black hole system. So this thing is equal to the size of the message, the dimension of the message divided by the dimension of the radiation. Okay? And so it's controlled by the ratio of the dimensions, and which is not the number of qubits. The dimension is exponential to the number of qubits. So this is like, let's say they're actually qubits. So it's 2 to the power of the number of message qubits minus the number of radiation qubits.
Is the number of photons radiated finite? In the soft modes, for instance, is there an infinite number of photons?
Oh, I don't know how to think about that.
It is a model, but roughly you take every temperature, Hawking temperature.
This is a very subtle problem. This is the kind of crude thinking that I get into trouble in my way.
So it is shocking. It is shocking how close this comes to the answer.
Maybe, but this wouldn't convince me. Maybe something.
Okay.
This didn't convince anyone, but it's a good, it's a good thing to
So the point here is that you need to collect just a few more Hawking modes, more than the size of the message. Like let's say you wait for this for 5 more steps, and then to extremely good accuracy.
because assume that the innards of the black hole are a unitary transformation, which is the,
Well,
in a sense, the key to the issue.
Well, no, sorry. But that's the thing that we want to end up with. And so they're assuming the answer and seeing what consequences that would have. So this is part of, as I said, the consequences of unitarity, right?
Yes, I agree with you. I was saying, this is a consequence. It doesn't prove that actually the black hole is unitary, because you're simply assuming that and seeing it.
Okay.
Still, I thought, going from unitarity to this also is, you would like to see, right? Why is it that unitary evolution, one unitary you could imagine is just decoupled unitary evolution, and then this will not happen. Right? Say that
Yeah.
wouldn't necessarily imply this, right?
Mhm.
This is some genericity of unitary transformation that is.
I think if it were sufficiently mixing in its unitarity, which his random tensor in a sense does,
Yeah.
then he's showing that it implies it.
Yeah.
But you would also want to ask why is it that the black hole evolution is unitary?
Yeah.
That's a separate question. And then once we show
The standard information paradox,
what
the
that
black hole.
evolution is unitary, correct. And that is the information paradox. If you show that, you've solved it.
Sorry, just a couple of questions. What is the one measure, just very quickly?
The Haar measure.
The one there is,
So here I was imagining the Haar measure.
yeah. But that norm is
Oh, the trace norm.
trace, just a normal.
Yeah, the trace norm. Yeah.
And where does the unitary come in? It is in row. You mean at each step you have the unit?
Exactly. Okay. Now, okay. So we understand how many qubits we need to collect in order, at least in this model, to get this condition to be true. But now you can ask, how random does U actually need to be? So if it's a Haar random unitary, then the number of steps it takes to implement this thing grows exponentially with the number of qubits, and that's really long. One should expect you expect information to come out of a black hole very quickly, and so it turns out that there's another class of unitaries that guarantee this feature, and these are called two designs, or often called a scrambling circuit. And these are circuits with logarithmic depth. So Haar circuits have exponential depth. These have logarithmic depth. Depth goes as the log of the number of qubits of the black hole, which, if you were sort of to translate this in terms of the black hole story, then it would say that there's a time t, which we call the scrambling time, which should go as the logarithm of the Bekenstein-Hawking entropy. Okay?
This is less random compared to the above one?
Say that again. Yeah, this is less. I'll explain in what sense. First of all, let me just fix the units here. There should be some beta here. Okay. So the takeaway here, the takeaway from this story is that the information comes out if you collect a sufficient amount of radiation, and you need to wait a time, which is the scrambling time. This would be sufficient amount of time for the information to come out.
Sorry, I missed this last part. I was just trying to process. So, had it been hard unitary, you say the number of steps would be exponential in the n qubits.
Yes, assuming you work with local gates.
Okay.
So you have some set of qubits, and you're working with gates like this.
Oh, I see. Each time you work with two. Okay.
Yeah. So the number of steps, it takes an exponential. Obviously, if you're allowed to act on everything at the same time, I mean, you can go from any state to any state.
Okay, I completely, okay.
Yeah.
And then you said, but then you can do better, is it? And just repeat that last part.
A two design is an ensemble. So it's let me see. So the definition is, so when you average over two design, this thing is going to, see, how would I write this? Yeah, well, maybe say it in words. It's an ensemble where it is equal to the Haar ensemble for moments up to u squared. So when you're computing, for example, integral du, it involves u dagger, but not any more powers of u. So an ensemble that agrees with the Haar measure up to this number of u's is called a two design.
I see. Up to just two of them.
Yeah, two u's and two u daggers. They have I, J, K, L, blah, 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 blah.
And if that's the case, then it's good enough. You get the information out
Everything I said follows.
on a time scale, on a number of steps of order log of.
That's right. That's right. That's right. Okay. Okay.
What did you use that was after the page time or something? Did you use that?
I use that here, where I started with LR being maximally entangled with BLBR. Okay. Okay. So now let's go back to.
So this local, so where is it that if you are assuming this Haar unitarity, unitary ensemble with a Haar measure, how does it come out that it needs to be made out of these local gates?
I'm just saying. Well. Let me see. I mean, this is just intuition from what you're able to do sort of in the lab. One can't act. I mean, you have a bunch of qubits. You can only act on them a few qubits at a time.
No, but I thought what you want to show is the equivalence of this to the Haar measure on the space of unitaries. So how is Haar measure on the space of unitaries related to what I can do in the lab?
No. So what is a unitary is this entire the Haar unitary is this entire thing constructed of these small guys. Well, maybe I'm not being clear here. Can you ask your question again?
So this Haar unitary, I thought by that you mean an ensemble of unitary matrices
Yes.
with a Haar measure. So this du, for example,
Yes.
this integral is
Yes.
with a Haar measure,
Yes.
and you're saying that consists of unitary transformations which are local in some sense. So I don't quite see this connection.
So we said that a Haar random unitary takes an exponential amount of time to implement, assuming you act only with local unitaries. Right? So this was a statement.
Oh, so there was an assumption in addition to them being Har.
Yes, yes. Okay, so
So in conclusion, your two designs are more random compared to the hard randomness that you had.
no. The point here is that a two design is sufficient for two things: getting the information out, getting that. Second, within a time which grows logarithmically with the number of qubits. That's all you need to take away from this discussion.
The time scale that you require for two designs is log of n roughly, log of the entropy.
Yeah?
Whereas the earlier you needed exponential times.
No, I'm saying
In the hard randomness you needed exponential times.
yes.
And we also know that for maximally chaotic systems in finite temperature, we can get the information out at more, if we want to get it out in the quickest possible way, then that would be this log.
Yes. This suggests that, and it might be, well, so actually I proved it
You
here.
cannot say that two designs are more random as a random tensor model.
Sorry.
Giving the information out much quickly compared to the other one.
It's a better scrambler.
Oh,
It is mixing it faster.
Could I say what I've understood and maybe
please.
that if you want to implement this complete whatever Har thing with two gates, that takes a lot of time.
Yes.
If you want to implement these two designs with two gates, that takes less time.
Yes.
Two designs are sufficient to get the information.
Yes.
Yeah, there's no worry.
Thank you for
Two
summary.
design does enough of the randomization so you can get the information.
Yes.
The definition of this two design ensemble was that it agrees with the Har ensemble when evaluated on this two.
Yes.
This moment.
Yes.
Right? So in particular, Har ensemble is a solution to that.
Which is not
Yes.
that you can actually for
Yeah. The Har ensemble is sufficient to get this answer.
No. So two design.
Yeah.
By definition,
Yeah.
something that agrees with the Har ensemble on this, right?
Up to this, yes.
Up to this. So
Yes.
Har ensemble in particular is a two design.
Yeah, sure, in the trivial sense, yes.
But then that is not doing the job.
But it is doing the job, but at a much it takes much longer to implement.
Yeah, but I thought your statement is that you need to design ensemble to
Uh,
do a log job, right?
No, okay. How about this? Let me define the two design as it agrees with Har only up to second moment.
That's not a good definition. You can go very close to Har, not being Har.
Sure, yeah, that's a bad definition. But
But you're saying this is correct definition? This does the job? Log
This
job,
definitely
even
does.
if you go a little bit away from Har measure.
no, the statement is that even if you go very far away from the Har measure for higher moments.
Har measure is not doing the job, right? It's doing an exponential job.
No, it depends on what the job is you're trying to get. If the job is to just get that the density matrix factorizes, then Har gets it, does it for
The
you
job is to make it factorize in log time.
in log time. Then two design is better than Har.
Yeah, but we thought Har measure is a particular case of two design.
No, but I mean, you can find an ensemble which disagrees as much as you want from Har for higher moments, but it agrees only up to second moment, and that will give it to you.
So there exists something.
Yes,
Okay.
yes.
But, sorry, you should really go on, Ahmed, but Indranil was asking, just let me paraphrase it like this, that had you allowed yourself unitaries that acted on, all the legs, that is half and half,
Yes.
then of course you could have done it with a random unitary in one shot,
Yes,
right?
but this is a sort of a locality assumption in some sense, and it seems more motivated physically.
And then we can talk later, but the fact that the chaos bound exponent also cares about a similar log,
Yeah.
does it suggest in some sense that there's a version of this locality going on for real black holes? I mean, that was the...
That's the intuition.
yeah.
Yes.
That would be interesting, if one could build on.
Yeah. I think this question has been studied by Dan Roberts, Xiao Liang, and other people
I see.
of computing these 4-point functions, assuming that you have Benny Yoshida, assuming different different unitary ensembles and seeing how that affects correlation functions and decay and so on and so forth.
I see.
So
In
the-
some model, SYK itself.
No, just quantum mechanics.
C
Okay.
and Roberts.
That's right. Oh, well, there are a few. Anyways. Next. Okay. Okay, now let's talk about regular physics again. Okay. So information does come out. Now, this brings us to the idea of black hole complementarity. Now, so the point is that if we assume that black holes do not lose information, then it seems that the observation is that we seem to run into the opposite issue, which is that black holes duplicate or clone information. And this is clear in the following picture. Not sure where to draw it, maybe here. I had to do this. That was me.
I thought it was you, right? You.
Yeah, it was me. So that entire story that we just went through just says that if I throw information into the black hole, at some point it should appear in the Hawking radiation in the bath. Okay? So it seems, I mean, from this picture, it looks like information has been cloned.
Because you continue to slice all through space.
Yes, exactly. So here's a space-like slice where the information appears in two places at the same time. In particular, something that can happen. So in our case, actually, the singularity is not here. I'm assuming that this thing is stable. So the idea is that two observers in the left and right baths should be able to, in some sense, distill this information here, capture the capture the qubit or whatever subsystem of the radiation that contains the information about this message, and jump into the black hole and have in their lab two copies of the same quantum state, right? So there's the message here, and then there's the message that they bring with them from the Hawking radiation. So they can see cloning. Lenny Susskind and friends wanted to say that such an experiment was sort of impossible to conduct, right? So they basically say if you wait a scrambling time before trying to catch up to get the message, right? So we said that if you throw the information in, you need to wait a scrambling time before the message comes out. So if you do that, you wait a scrambling time, you collect the radiation, and then you jump in, then somehow, actually now let me put back the singularity. Somehow you can never catch up to it.
The guy would have died first.
The guy would have died, or the message would have hit the singularity before they can catch up to it.
Or you would need Transplanckian wavelengths.
Good. So their argument was that, as Sandeep just said, you need control over Transplanckian physics to actually be able to conduct this experiment. But I actually think that that's a red herring. I don't think that's the correct argument, and I will come back to this later.
Sorry, I thought you said that cloning is disallowed by linearity.
That's right.
But here already you have done the cloning. It's the fact that they are unable to talk to each other.
Exactly.
What's
So
the problem? I have already done the cloning. Right? That's a bad
no, but the question is, can a single observer see the cloning? That's why it's called black hole complementarity. So complementarity is the idea that you can, measure position or momentum. You can't measure both because these observables do not commute. And so that's the same statement here, that you can only see the information either outside or inside. You can never get two copies of the information. Those are the set of words that they were using.
Sorry, but those two observers which are outside,
Yes.
they cannot talk to, they are unable to.
Well, even if they talk to each other, there's no problem. The information is not, but the cloning is not in that I have something here, something there. No, the information is in the union of these two. I just drew it like this because, I mean, there's no reason why it should be on one side versus the other. Actually, no. Actually, maybe I'll talk about this later. Actually, I think it appears only on this side. But let me talk about that later.
So when they move, do they not have to move along some space-like slice?
Who? The observers?
These guys when they're coming in.
No, I mean, they have to go in a time-like slice.
Yeah, but it seems like they cannot do that.
Why? I
Very
mean,
fast.
yeah, we have to go.
See both the inside and the, I think that's his
That's the
point,
point.
that, it's at two places, but you can't no one observer can access it.
Yeah, yeah.
So it's okay to violate linearity in quantum mechanics as long as you don't see it?
That was the claim. That was.
That's funny.
I agree.
Yeah, but it would be the statement that having a state on a Hilbert space like this is wrong.
Exactly. Exactly.
You have this slice and it's an
Exactly. This assumes somehow that you have a tensor factorization of the Hilbert space like this, and then in that sort of way of thinking about it, you run into a paradox. In any case, I will have more to say on this later. Now, let me state the famous postulates of complementarity. So they were trying to come up with rules for black hole physics, and they came up with the following postulates. The first is unitarity. The fact that black hole formation and evaporation is unitary, which in this case is a statement that the Page curve is followed. Second postulate is that we have semi-classical physics outside. Okay, the observations of an observer outside is governed by semi-classical physics.
Can we amend that to say, including very small violations of locality which are e to the minus gn effects? I mean, just to make sure.
Minus 1 over gn.
Okay, 1 over gn. That's part of it, right?
Non-locality. Sure.
Okay.
Postulate 3, that the black hole Hilbert space at some given mass is finite and given by e to the Bekenstein-Hawking entropy. Okay? And yeah. And so these were the postulates of complementarity, and everyone then forgot about this problem. Okay, but
Why you are allowing for non-locality here?
no, that's just for Sandeep.
Well, because that's probably how it will be solved. I mean, whatever,
Okay.
the information will come back out from the inside.
Oh, but that's a statement about outside, right?
Yeah, but I mean, okay, but I mean, the physics outside is connected to the inside through e to the minus 1 over gn.
Okay. Okay.
That's all I'm saying.
Okay. 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 So this naturally leads us to the firewall paradox.
So maybe locality is violated in some small way, but causality should be exact.
Yes. Yes.
And these two would have to be very carefully managed.
Yes. I agree.
But locality and causality goes very close, right? Like you require locality to make it causal.
Okay, then we'll get into all these questions, but I mean, there's a precise, perhaps, notion of unitarity for S matrices, and anything we can derive from that. But to say on a space-like slice what is causal, you need a well-defined notion of a metric, etc. Right?
Exactly. So causality for the S matrix.
Yeah.
As an exact.
Right. But their notion of semi-classical physics was that local effective field theory was approximately correct, right?
No, I understand. But the kind of violation of locality you have should not lead to violation of causality for the S matrix, no matter
Yes.
what. Okay.
Yes. Yes.
Then we get but for the S matrix, yes.
For the S
some local provocation.
No, but like we're talking about, right? It shouldn't be possible to send something in, that's cry minus, and get something out even a little bit before the light comes. That's what I mean. That's a completely precise physical statement. And it should be exact.
Indeed. Okay. Now, so this leads us to the firewall paradox, which is the claim. The first claim is that there's an implicit postulate here assumed in this story, which we called postulate 4, which is what we call the no drama postulate, which is simply the statement that we have a smooth black hole horizon. Okay, so I mean, implicit here is that we can actually jump into the black hole, right? But the point now is that there's a conflict between these postulates, and to see that, let's again consider our evaporating eternal black hole at late times after the page time, and where the von Neumann entropy, I guess it's hidden now. So we're somewhere here. The von Neumann entropy of the radiation is saturated and is not growing anymore. And the idea now is to consider the next Hawking mode to come out. So let me draw the space-time again.
I have a question. So if, let's say, Alice and Bob from two sides, two sides, they jump in, but with their respective pieces of fluid information, and if they never manage to meet and get crushed by the singularity or whatever, why is it important to have this no drama postulate? Because, and that will make no difference as to whether some observer can compare their own pieces of information.
Sorry, isn't it the question you assume that they can jump into the black hole?
Yeah, so even if they can, obviously if they can jump into black hole, then obviously it has to be smooth.
Yes?
But jumping into the black hole itself, does not cure the full thing, because if even if the black hole were to be smooth, if they're crushed by the singularity,
Yes?
they can never compare their own pieces of information.
Yes?
So the cloning paradox, from point of view of one observer, does not arise. So why is it absolutely essential to have this postulate?
So, the idea of black hole complementarity first assumes that the information appears in two places at the same time.
Nice.
So one being the inside of the black hole, therefore the inside is there.
Okay.
So yeah.
I see, okay, that was in the collapsing black hole scenario.
Yeah.
Where,
Which is
one
also
piece
here.
information appears inside the black hole.
Yes. Okay. Should we wait for, no, okay. I'll review it when Sandeep comes back. Okay. Already knows this. Okay. Okay, so let's consider the next Hawking mode to come out. That's A here. And it also has its interior partner, A tilde. This is just by Hawking. Now okay. From the page curve, the thing that we gather, which is, you can think of it as a result of postulate 1, that SAB, B being the bat, the union of the bats, must be less than or equal to SB. Okay? So it's a statement that A has to be entangled with a subsystem of B. The reason why, so you might have said that that it has to be equal to SB because the entropy is constant, but there's this issue that there are things falling in as well. Okay, so really you have to say that. Okay, so by postulate 1 we have SAB is less than or equal to SB. From the no drama postulate, postulate 4, we know that we have to have the Hawking state, the vacuum on the horizon. That's a statement that SAA tilde is equal to 0. That's one part of the statement. Another one is that SA is greater than 0. So really there's entanglement between A and A tilde. It's not a product state of A and A tilde. Okay, postulate 2 says that this mode A is sort of, it's the same mode along this entire trajectory, as in nothing funny happens to it. There's no non-local effect that somehow switches the information of A with something else. Just semi-classical, just regular propagation on some fixed background. And the claim is that now we have a contradiction. Consider strong subadditivity.
Sorry, your P1, I thought is the same model that you discussed yesterday. I thought SAB was increasing, right, with the time. Sorry, I missed. Is the same model as yesterday?
Yeah, it's the same model. Yeah.
So I thought as the time goes by, the entanglement entropy increases, right? So was the SAB?
No. But we're assuming we have unitarity,
Oh, after
right?
the.
Yeah. So we assumed that. So postulate 1 is that we have unitarity, so we have that page curve.
So I didn't understand the consequence of P4. Why? I thought that A and A tilde were like the right and left Rindler
Yes.
oscillators.
Yes.
So then I thought they were maximally entangled rather than.
Yeah. That's what this statement is.
Pure state. A tilde is pure.
Yeah.
So maybe I'm missing the notation. I mean.
So for simplicity, so I have something like this: is AA tilde plus 1 AA tilde plus, well,
Oh.
yeah. So whatever, it's e to the minus beta n omega n a n tilde a tilde, or n a tilde, right? Just the usual Hawking state. Yeah, it's a pure state, exactly. So now let's apply strong subadditivity.
He's saying outgoing radiation, the mode purifies the radiation. At the same time, the ingoing mode adds it.
Yeah.
The outgoing tends to purify radiation.
Yeah, because you're after the page.
That's right. The idea is that A can't increase the entropy of B.
The left-hand side is after this gas come in, and this was before that.
Yes. Okay, so let's apply strong subadditivity for the following 3 regions. So S A tilde B plus S A is less than or equal to S A B plus S A tilde. Let's apply the postulates. From postulate 4, we know this is 0.
And just to be totally clear, you're assuming there's a tensor product of 3 Hilbert
I am.
spaces.
That's yes. So that's the assumption. I'm not sure in which postulate I would put this, or whether it's a different postulate. But yeah, that's definitely an assumption. The fact that A tilde is equal to 0 means that this thing is actually just equal to SB, because A and A tilde are not entangled with anything. They're not entangled with B, using this postulate. And so, and from postulate 1, we know that this thing is less than or equal to SB. And so we have SB plus SA is less than SB. And so SA is less than or equal to 0. Okay? And, but we just said that SA is greater than 0. So this is in contradiction with this guy. Okay. And so now, so this is the firewall paradox. And so the idea is that one of these postulates has to give. And it seems like the least undesirable one to give up is postulate 4. I mean, we want semi-classical physics outside. We definitely want unitarity, and black hole hyperspace is finite. This is not that essential for us because we're outside of a black hole. At least that's what we think.
So could I ask, wasn't it inherent in the notion of complementarity that the factorization of the Hilbert spaces must be wrong?
Yeah, I was about to say the same thing. That actually, although you listed this, whole idea of complementarity was that you can't talk about the inside and the outside, right? You use the word or, but not and, right? So doesn't that mean that?
How about this? I think that touches on the issue of whether you should expect semi-classical physics to work in the light cone of any observer. So you might say that for any observer, you can draw a light cone, and you say that the physics on any slice within that light cone is governed by usual semi-classical physics with a tensor product factorization. This thought experiment tells you that that assumption is wrong, right?
Just because the horizon is inside the light cone,
Yeah. So
but not accessible to the outside, right?
So let's say B. Let's say for now that the radiation, we only care about the radiation here. So B is just this. Here's a light cone of an observer. I can collect all three systems. I guess maybe I should draw it like this. And they can see the
Okay, but
paradox.
I see your point. Yeah, that's a good point. But I mean, the idea of complementarity still was that there's something important about a black hole horizon, and you can't talk about the stuff inside and outside together, right?
Yes, yes.
So if we at least privilege the black hole horizon, then
Yeah, but I really think in implicit, actually implicit in, no, not implicit. I think that the idea is that you cannot, is that things outside of observers' light cones can possibly fail to commute. But within a single light cone, everything should be fine. I mean, that was the idea, right? The idea is that an observer trying to come in to catch up to this information just can never catch up to it. So the thing that doesn't commute with something here that he has in his hand is because that thing is outside of his light cone in a sense. Okay.
Wait, so how did this observe? Oh, I see.
Okay.
you have to say, yeah, I understand. I mean, you're saying you can collect your in your picture, your A qubit and send it back in, and then
Yeah.
it's entangled both with B and with A.
Exactly. Exactly.
But it does leave open for the possibility that the interior, in a sense, is not an independent Hilbert space, right? Because that could square up. We'll have to then say how does an approximately local interior arise and so on. That's a fair point.
Yeah. And this is something we'll touch on later. But so no, so
Extend the commute. That is the, like, when you say that for this observer, the things that are space-like separated on the slice, they are commuting. To what extent they commute? This is a
yeah, I think we'll touch on this point later. For now, the result here is that there's a firewall that appears at some point. This experiment that led to the firewall paradox is something that happened that can happen anytime after the page time. And so it seems like maybe the page time is the trigger for the creation of this firewall. So here's a t equals 0. At some, let's say this is the page time. This seems to say that the horizon at the page time is singular. So that means we have a firewall here, like this. But this is crazy. The reason is there's nothing privileged about this point. This system is boost invariant. So I could have sliced things in a different way, and the firewall could be here, or here, or here, or maybe I could go backwards in time, you know? So this entire thing is singular.
Here you're using that firewall is horizon by horizon.
Exactly. And so and I can do this experiment backwards in time as well. So this seems to suggest that the thermal field double is actually not dual to the wormhole, but rather dual to this object. And that's just crazy. Okay. Okay. Let's see. The final thing in this set of notes is maybe I should stop. Well, no, this is the final thing, so let me say it. let me just mention a.
After you do this, we could have a little tea break.
Okay.
Avoid
Okay. Okay.
if you would like.
Okay. Okay. I have my banana, so I can do that. So there's a. Yeah. Let me mention just a single possible out, namely.
I mean, when you were entertaining this firewall possibility, things could be crazy in the interior.
I mean, there is no interior.
Okay.
Yeah. Yeah. So there is a possible out, which is often goes by the name of ER equals EPR, or A equals RB, or what we've been talking about, some sort of non-locality. That's essentially what this is, which is basically the idea that somehow when you build enough entanglement between the black hole and the exterior, you spoil this notion of having a nice semi-classical feature of local factorization of the Hilbert space on some fixed geometry. And somehow, A tilde is now secretly, I should write it here actually, that A tilde is secretly part of B. Okay? There's some non-local identification. And we can see, check very briefly, that if you assume this, then you don't run into an issue. The strong subadditivity argument doesn't apply. And the question then is, are these two statements, which I have over there, that the P1 and P4, can these two statements be consistent? And the answer is yes. Let me give you an example of that. Let's say we write B as equal to A tilde times B tilde. So I'm just factorizing the Hilbert space of B into these two things. There's some factorization that looks like this. From S A tilde equals 0, we get that the density matrix of A tilde B tilde is simply equal to the density.
Lose the entropy of it.
Exactly. And this is a pure thing times B tilde. So this follows just because A tilde is because of this. And then so now we can trace over A on both sides. So then the density matrix of A tilde B tilde is just rho A tilde tensor rho B tilde, which implies that the entropy of B is equal to, this is equal to B, remember, because of this. Now compute the entropy using this density matrix. You find the entropy of B is equal to this one?
Yeah.
It comes from this. You trace over A on both sides. This thing is now, because this is a tensor factorization, this implies that the entropy simply adds.
You have no entanglement between A tilde and B tilde, is it? I mean, if rho
Correct. Because SA tilde is 0, so there's no entanglement between A tilde and B tilde. That follows from from postulate 4.
I thought it was just an assumption that B was.
This is an assumption about the Hilbert space of B.
Oh, I see.
That it's a tensor factorization of A tilde B tilde.
State is also tensor factorized now.
Yes,
That is an assumption, right?
that follows from this statement.
Okay, that's what I'm trying to internalize. So, because there's no entanglement between A and A tilde,
That's
Yes.
monogamy of entanglement of A.
Yes.
I see. Okay. And now, and therefore, yes, that rho A tilde B tilde. Let me get this right. I mean, so there's no entanglement between A and A tilde, but there can be entanglement between.
No.
A tilde as union.
A is entangled only with A tilde.
Maximally entangled.
Oh, yeah. I see.
That's why this thing factorizes in this way.
Okay.
Okay? Yeah. So then this means that this thing is actually greater than S B tilde, because this thing is some positive number. But also, from the same statement here, we also deduce that S AB is equal to, so this is rho AB. Right, because this thing is B. Computing the entropy here, we will get S A tilde plus S B tilde. And therefore, this is just equal to S B tilde. And we conclude here, so take this equality, plug it into this inequality, and we get SB is greater than SAB. Yeah, great. I guess this could have been equal to, because this thing could have been 0, but it's not 0, but okay, whatever. Which is consistent. It is consistent with P1. Okay. P1 was SAB. Has to be, is it less than or equal to SB? Oops. Okay. So this is just a check that if you assume that A tilde is a part of B tilde, then things can be consistent.
Sorry, I understand the algebra. Can you just say once, like what's happening? What did you do?
Oh, I assumed that A tilde is part of B.
What does it mean? Like A tilde is part of B?
So A tilde is a mode behind the black hole horizon.
Right.
B is the modes far away.
B are the boundary modes.
No, B are the Bath modes.
B are the bottom.
Yes? And now I'm saying that this idea of ER equals EPR, one way to resolve the firewall paradox is to say that there's some sort of non-local identification between things behind the black hole horizon and things far away. Okay? And that's a statement that A tilde is secretly part of B. This non-local identification says that the interior is part of the exterior. And so I just gave an example. I said, let me say that B can be you can write it as a tensor product of A tilde and the complement B tilde. And I show that that indeed you don't run into a paradox by assuming the postulates, P1 to P4. I didn't give you the physics of how this is true. I just said, let me assume it. And
so when you say A tilde is part of B, that means entire black hole inside is can be written in terms of B, or just the Hawking modes can be written?
Ultimately, you want the entire thing, but for now, let's just say just A tilde.
So that will already make the entire inside to be unitary, all those things automatically, right?
How this resolves the unitarity issue, we'll get back to later.